Hi everyone. Welcome. It's good to have you here tonight. Wherever you are right now, lying in bed, resting on a couch, settling into a quiet room. I'm glad you found your way here. Tonight, we're going to talk about something very simple. Something so ordinary, so constant, so quietly present in every single moment of your life that you almost never think about it. We're going to talk about gravity. Specifically, we're going to talk about why Earth has gravity. Not in a complicated way, not with confusing numbers or difficult equations. Just slowly, gently taking our time. We'll move through the ideas like water moving through a shallow stream, unhurried, clear, soft. There's no rush tonight. If you fall asleep before we get to the end, that's perfectly fine. That's a good thing. Actually, the ideas will still be here, if you want to come back to them. So let's begin very simply. Let's begin at the beginning. You already know what gravity is, in a way. You've known it your whole life. It's the feeling of weight in your body, right now. Notice it, just for a moment. Feel how your body rests against whatever surface is beneath you. Feel how your limbs settle downward, gently without any effort on your part. That's gravity. It's always there. It never stops. When you were a baby, just minutes old, gravity was already at work, keeping your small body settled and grounded. When you sleep tonight, gravity will hold you softly in place, the same way it has every night of your life. Gravity is, in many ways, the most constant thing about being alive on this planet. It never wavers. It never takes a break. It never changes its mind. And yet, most of us go through our entire lives without ever really asking, where does this come from? Why does Earth pull things toward it? Why is there gravity at all? These are the questions we're going to sit with tonight. Quietly, slowly, together. Let's start with the most basic answer, the simplest version. Earth has gravity because it has mass. That's it. That's the core of it. Everything that has mass also has gravity. You have mass, so you have gravity. The cup on your nightstand has mass, so it has gravity. The moon has mass, so it has gravity. The sun has mass, so it has very strong gravity. Mass and gravity go together always. You can't have one without the other. Wherever there is mass in the universe, there is a gravitational pull, a gentle reaching outward, in every direction like a slow, invisible breath. Now, the reason Earth's gravity feels so strong to us, the reason it's enough to keep our feet on the ground and hold the oceans in their basins and keep the moon circling above us, is simply because Earth has a lot of mass, a very, very large amount of mass. Earth weighs approximately 6 times 10 to the power of 24 kilograms. That's a 6 followed by 24 zeros. We don't need to picture that number exactly. It's simply enormous. And all of that mass gathered together pulls on everything around it. Pulls on you, pulls on the air, pulls on the water, pulls on the moon. That pulling, that gentle, constant reaching, is what we call gravity. The idea that mass creates gravity is something people have understood in different ways over a very long time. But the person who first described it clearly, who wrote it down in precise mathematical language, was Isaac Newton. You may have heard of Isaac Newton. He was an English scientist who lived in the 1600s. There is a famous story, probably more legend than fact, but a pleasant story nonetheless, that Newton was sitting under an apple tree one afternoon and an apple fell. And he wondered, why did the apple fall downward? What force pulled it toward the earth? He began to think deeply about this. And over many years of thought and calculation, he worked out a beautiful, elegant law. He called it the law of universal gravitation. The word universal is important here. Newton wasn't just saying that the earth pulls on apples. He was saying that every object in the entire universe pulls on every other object. Every piece of mass reaches out invisibly across any distance and tugs on every other piece of mass. The apple pulls on the earth, just as the earth pulls on the apple. You pull on the moon, just as the moon pulls on you. Of course, The moon has much more mass than you do, so its pull is much stronger. But the pulling is mutual always. It goes in both directions, every time. This was a remarkable realization. Before Newton, people thought of gravity as something special about the Earth, a local property belonging only to our world. Newton showed that gravity is a universal property. It belongs to everything. The Earth has it. The Sun has it. Distant stars have it. You have it. It's everywhere, always in everything. Newton described the force of gravity with a simple formula. We're not going to do any math tonight, but it's worth understanding the ideas behind the formula in a quiet, gentle way. The formula says this: the force of gravity between two objects depends on two things. First, how much mass each object has. Second, how far apart they are. The more mass an object has, the stronger its gravitational pull. And the farther away two objects are from each other, the weaker the pull between them. This makes a kind of intuitive sense if you think about it. A mountain has more mass than a pebble, so a mountain's gravity is stronger. Earth has more mass than the moon, so Earth pulls on you more strongly than the moon does. And distance weakens gravity. If you were somehow lifted up, high above the Earth, into space, you would feel gravity becoming weaker and weaker the farther you traveled. It never completely disappears, not in Newton's description, but it fades slowly like a voice calling from farther and farther away. This relationship between distance and gravity has a specific quality. The force doesn't just decrease as you move away, it decreases with the square of the distance. This means that if you double the distance, the gravitational force drops to 1/4. If you triple the distance, it drops to 1/9. It fades quickly, in other words, not instantly, but quickly. Newton's formula worked extraordinarily well. With it, scientists could predict the movement of planets, the paths of comets, the timing of tides. For over 200 years, Newton's description of gravity was the best we had, and for most everyday purposes, for building bridges, for launching satellites, for predicting where the moon will be, it still is. Let's pause here for a moment. Take a slow breath. Feel the weight of your body. Feel gravity doing its work quietly in the background as it always does. We've covered the basics now. Mass creates gravity. More mass means more gravity. Greater distance means weaker gravity. These ideas are simple, but they're profound. They explain why you stay on the Earth. They explain why the Earth stays near the Sun. They explain why galaxies hold together across unimaginable distances. Simple ideas, enormous consequences. Let's continue slowly. To understand Earth's gravity more fully, it helps to understand a little bit about what Earth is made of. Because gravity comes from mass, and mass is matter, physical stuff. Understanding Earth's physical structure helps us understand where all that gravity-creating mass actually lives. Earth is not a uniform ball of rock. It has layers, like an onion in a sense, or like a very large, very hot peach. The outermost layer is called the crust. This is the layer we live on. It's relatively thin, in most places, somewhere between 5 and 70 kilometers thick. Compared to the whole size of the Earth, the crust is like the skin of an apple. Very, very thin. Beneath the crust is the mantle. The mantle is much thicker, nearly 3,000 kilometers deep. It's made mostly of silicate rock rich in silicon and oxygen. The mantle is solid, but it moves very, very slowly. Over millions of years, portions of the mantle flow like an extremely thick, sluggish liquid. Beneath the mantle is the outer core. The outer core is genuinely liquid, a vast ocean of molten iron and nickel swirling slowly in enormous lazy currents. This liquid iron is what generates Earth's magnetic field, and at the very center of the Earth is the inner core. The inner core is solid, a dense ball of iron and nickel, roughly the size of the moon. It is extraordinarily hot, somewhere around 5,000 degrees Celsius, roughly as hot as the surface of the sun. And yet it remains solid. It remains solid because of the enormous pressure pressing in on it from all the mass above. Pressure so great that the atoms cannot move freely. They're locked in place, vibrating slowly in their positions, unable to flow. All of these layers, crust, mantle, outer core, inner core, contribute their mass to Earth's total. Together, they make up that vast number we mentioned earlier, 6 times 10 to the 24th kilograms. All of that mass layered together creates the gravity you're feeling right now. Here's something interesting to consider. While you rest, gravity doesn't just pull things toward the Earth. Gravity also shaped the Earth itself. Earth didn't arrive fully formed like a sculpture. It was built up gradually over a very long time from much smaller pieces. About 4.5 billion years ago, our solar system was a vast spinning cloud of gas and dust. This cloud began to collapse inward, drawn together by gravity. Most of the material fell toward the center, where it became the sun. But some of the material, the leftovers you might say, remained orbiting around the young sun. This leftover material gradually clumped together. Particles stuck to particles. Small clumps merged with other clumps. Larger bodies absorbed smaller ones. This process is called accretion. The word comes from a Latin root, meaning to grow or to add to something. As these growing bodies got larger, their own gravity got stronger. And as their gravity got stronger, they could pull in material from farther away, which made them even larger, which made their gravity even stronger, which pulled in even more material. It's a feedback loop, a gentle, slow, cosmic snowball effect. The young Earth was built through this process over tens of millions of years. Piece by piece, clump by clump, it grew. And as it grew, gravity did something important. It pulled the denser materials, heavy metals like iron and nickel, downward toward the center. And it left the lighter materials, silicates, oxides, floating higher up. This is called differentiation. The Earth sorted itself out under the influence of gravity. Heavy things sank, light things rose, and that's how we ended up with that layered structure. The iron core, surrounded by the rocky mantle, surrounded by the thin outer crust. Gravity organized it all, quietly, patiently, over millions of years. Gravity also determines the shape of the Earth. Earth is roughly spherical. It's not a perfect sphere. It bulges slightly at the equator, but it's close. And the reason it's roughly spherical is gravity. Think about a large quantity of material, rock, ice, water, whatever, gathered together. Gravity pulls every piece of that material toward every other piece. It pulls from all directions equally. And when you pull a blob of material inward from all directions equally, the shape it naturally takes is a sphere. A sphere is the most compact, efficient shape, the shape that minimizes the distance between every particle and the center of mass. This is why planets are round. This is why moons are round. This is why the sun is round. Any object with enough mass that its own gravity is the dominant force shaping it will naturally tend toward a sphere. There's actually a name for this property. Astronomers call it being in hydrostatic equilibrium. It's a long phrase. Don't worry about remembering it. What it means simply is that the object's gravity has become strong enough to pull it into a roughly spherical shape. Small objects, asteroids, rocks, irregular chunks of ice, don't have enough mass for their own gravity to reshape them. They remain jagged and lumpy, whatever shape they happen to be when they formed. But large objects, planets, moons, stars, are massive enough that their gravity smooths them out, rounds them off, settles them into that peaceful, efficient, curved shape. The Earth beneath you right now is a sphere because of gravity, the gravity of all that mass pulling inward from every direction for billions of years, shaping itself, organizing itself, finding its equilibrium. Let's think about falling for a moment, gently, without any anxiety attached to the idea, just as a physical curiosity. When something falls, when you drop a pen, when rain falls, when a leaf drifts down from a tree, it falls because of gravity, and it falls in a specific way. Near the surface of the Earth, gravity accelerates falling objects at a rate of about 9.8 meters per second per second. That's a bit of a strange-sounding phrase. Let's take it apart slowly. When something is falling freely, in the first second it falls, it's moving at about 9.8 meters per second. After 2 seconds, it's moving at about 19.6 meters per second. After 3 seconds, 29.4 meters per second. It keeps speeding up. Each second, it gains another 9.8 meters per second of speed. In everyday terms, that's about 35 kilometers per hour for every second of falling. So after 10 seconds of free fall, an object is moving at about 350 kilometers per hour. This rate of acceleration, 9.8 meters per second, has a special name. It's called little g, or simply g. It represents the strength of Earth's gravitational pull at the surface. Here's something beautiful about this number. It's the same for everything. A feather and a bowling ball, if dropped from the same height in a vacuum, with no air resistance, will hit the ground at exactly the same time. This was shown experimentally by Galileo, the Italian scientist who lived in the 1500s and 1600s. The story goes that he dropped 2 different cannonballs from the top of the Leaning Tower of Pisa, one heavy, one lighter, and they hit the ground together. The legend may be embellished. Historians debate whether Galileo actually did this exact experiment, but the result is true. Gravity pulls on all objects equally regardless of their mass. The reason this seems counterintuitive is air resistance. In everyday experience, a feather falls more slowly than a bowling ball, but that's because air is pushing back against the feather, slowing it down. Remove the air, do the experiment in a vacuum, and they fall at exactly the same rate. This was actually demonstrated on the moon. During one of the Apollo missions, an astronaut named David Scott dropped a hammer and a feather simultaneously on the lunar surface. The moon has no atmosphere, no air resistance, and both the hammer and the feather hit the ground at the same time. It's a quiet, lovely demonstration. A hammer and a feather falling together. Gravity treating them exactly the same. Now, Newton's description of gravity is extraordinarily useful, but in the early 1900s, a young patent clerk in Bern, Switzerland, began to think about gravity in a completely different way. His name was Albert Einstein. Einstein's new way of thinking about gravity is called general relativity. It's a beautiful theory, subtle and surprising in its ideas. We'll move through it gently. Newton described gravity as a force, a pulling force that one mass exerts on another, acting across space. Einstein asked a different question. He asked, what if gravity isn't a force at all? What if it's something else, something more fundamental? Einstein's answer was this: gravity is the curvature of spacetime. That phrase, the curvature of spacetime, sounds very abstract. Let's try to make it a little more tangible. First, what is spacetime? Spacetime is the combination of the 3 dimensions of space, length, width, height, with the dimension of time. Einstein showed that space and time are not separate things. They're woven together into a single fabric. That fabric is what we call spacetime. Now, Einstein's insight was this: mass bends spacetime. When a massive object, like the Earth, sits in spacetime, it creates a curve in that fabric, a depression, a warping. The classic analogy is a heavy ball resting on a stretched rubber sheet. The ball creates a dip in the sheet. If you roll a smaller ball across the sheet, it will curve toward the large ball. Not because the large ball is pulling it, but because the shape of the sheet guides it there. That's gravity in Einstein's description. Not a pulling force, but the geometry of space-time itself guiding the movement of objects. Objects in free fall, falling freely with no other forces acting on them, are actually following the straightest possible path through curved space-time. It's called a geodesic, and because space-time near a massive object is curved, those straight paths curve as well. This may sound like it makes things more complicated, but in many ways it simplifies things. It explains things that Newton's theory couldn't. For example, Einstein's theory explains why even light, which has no mass, is bent by gravity. In Newton's picture, this is puzzling. Light has no mass, so what does gravity act on? In Einstein's picture, it's natural. Light follows the curvature of space-time, just like everything else. This bending of light by gravity was actually observed during a solar eclipse in 1919. Astronomers measured the positions of stars near the edge of the sun during the eclipse. The stars appeared slightly shifted from their expected positions. The light from those stars had been bent by the sun's gravity on its way to Earth. The measurements matched Einstein's predictions precisely. It was a quiet revolution in our understanding of what gravity is. Let's stay with the rubber sheet image a little longer. It's helpful. Imagine a large flat rubber sheet stretched out evenly in all directions. Now imagine placing a heavy ball, say a bowling ball, right in the center. The ball sinks into the sheet, creating a deep, smooth depression around it. The sheet near the ball curves steeply downward, then gradually flattens out again as you move away from the ball. Now imagine rolling a small marble across this sheet. If the marble passes far from the bowling ball, it rolls in nearly a straight line. If it passes closer, it curves. If it passes very close, it curves sharply, maybe even spiraling down toward the bowling ball. The marble isn't being pulled by a mysterious force. It's simply following the shape of the sheet. This is analogous to how planets move around the sun. The sun, much more massive than any planet, creates a deep curve in space-time. The planets follow paths around the sun, not because the sun is pulling them with a rope, but because the geometry of space itself curves them into those orbits. The Earth, in turn, creates its own smaller curve. The Moon follows this curve, orbiting around us. Satellites follow this curve. Even the atmosphere, all those miles of air above us, follows this curve, held in place by the shape of space-time that Earth creates. And you lying there feel this. The ground beneath you is pushing against you, preventing you from following the natural curved path through space-time, which would be downward into the Earth. The Earth's surface is what you feel as weight, the surface pressing up against you. Gravity, in a sense, is the Earth's space-time curve trying to pull you through the floor. The floor is what stops you, and you feel that there's weight as the comfortable, familiar pressure of your body at rest. Let's drift gently to another consequence of gravity. Tides. You've probably seen tides, or at least heard of them. The slow rising and falling of the ocean, twice a day, in response to the moon's gravitational pull. The moon is roughly 384,000 kilometers away from Earth. That's a long way, and the moon is much less massive than Earth. But the moon's gravity is still strong enough to have a noticeable effect on the oceans. Here's how it works. The moon pulls on different parts of the Earth with slightly different strengths. The side of Earth closest to the moon is pulled a little more strongly than the side farthest away. This difference in gravitational pull across the body of the Earth is called the tidal force. The oceans, being fluid, able to move, respond to this tidal force. On the side of Earth facing the moon, the ocean is pulled slightly upward, forming a bulge. But here's the part that surprises many people. There's also a bulge on the opposite side of the Earth, the side facing away from the moon. Why? Because the solid Earth is pulled toward the moon more than the distant ocean water is. So relative to the Earth's center, being pulled toward the moon, the far side water gets left a little behind, creating a second bulge. As Earth rotates, different parts of the coast pass through these bulges. That's what creates the rhythm of tides, roughly 2 high tides and 2 low tides every day. The sun also contributes to the tides. Even though the sun is much farther away, it's so enormously massive that its tidal effect is about half as strong as the moon's. When the sun, Earth, and moon are aligned, during new moon and full moon, the tidal forces add together. These are called spring tides. Higher than usual, high tides. Lower than usual, low tides. When the sun and moon are at right angles to each other, during the quarter phases, their tidal forces partially cancel out. These are called neap tides. More moderate, less extreme. Tides have been quietly shaping life on Earth for billions of years. The rhythmic rise and fall of coastal waters creates unique habitats. Tidal pools, those small collections of water left behind as the tide retreats, have been important environments for life throughout Earth's history. And on a much longer timescale, the tides are gradually slowing. Earth's rotation, very slowly, almost imperceptibly, but over billions of years, the day is getting longer. Long ago, a day on Earth was only about 6 hours. Currently, it's 24 hours. Far in the future, it will be longer, still. All of this shaped by the gentle, persistent pull of the moon's gravity. There's something worth understanding here, a gentle distinction that helps clarify what gravity actually does. The difference between weight and mass. Mass is the amount of matter in an object. It's an intrinsic property. It doesn't change depending on where you are. Weight is different. Weight is the force that gravity exerts on your mass. And it depends on how strong the gravitational field is around you. Your mass is the same wherever you go in the universe. Your weight changes depending on where you are. On the moon, gravity is about 1/6 as strong as on Earth. So if you weigh 60 kilograms on Earth, which is to say if the Earth's gravity pulls on you with a certain force, you would weigh about 10 kilograms on the moon. But your mass would still be the same. Your body would still contain the same amount of matter, just less gravity pulling on it. On Jupiter, by contrast, gravity is about 2.4 times stronger than on Earth. The same person who weighs 60 kilograms on Earth would weigh about 144 kilograms on Jupiter. In deep space, far from any massive object, you would be essentially weightless. You'd float freely, feeling no gravitational pull in particular. But your mass would still be there, still the same. You'd still contain all the same atoms, all the same matter, just floating gently with no surface pressing against you. This distinction, mass versus weight, is useful to keep in mind. When scientists talk about the mass of the Earth, they mean the total amount of matter it contains. That doesn't change. Weight, on the other hand, is a force that varies with location. Gravity doesn't just hold you on the surface of the Earth. It holds the air, the atmosphere, that thin envelope of gas that surrounds our planet, is held in place entirely by gravity. Without gravity, the atmosphere would simply drift away into space. The molecules of gas would disperse outward, gradually thinning until there was nothing left. The atmosphere is about 78% nitrogen, about 21% oxygen, and small amounts of other gases. It extends upward roughly 100 kilometers before fading almost entirely into the vacuum of space. But most of the atmosphere is much closer. About half of all the air, by mass, is within 5 kilometers of the surface. The air gets thinner quickly as you go up. The reason for this is gravity. Gravity pulls the air down, compressing it near the surface. Higher up, with less air above pressing down, the compression is less, so the air is thinner. This is why mountains feel different. At high altitude, the air is thinner, less compressed, fewer molecules of oxygen per breath. It's harder to breathe. And the sky looks a deeper blue because there's simply less atmosphere above you to scatter light. The thinning of the atmosphere with altitude follows a smooth, gradual pattern. There's no sharp boundary where air suddenly stops. It just fades slowly into the near vacuum of near-Earth space. The official boundary of space, called the Kármán line, is defined as 100 kilometers above the surface. At that height, the atmosphere is so thin that it no longer meaningfully affects aerodynamics. But even above that line, traces of atmosphere persist. Satellites in low Earth orbit still experience very slight atmospheric drag. It's not much, but it's there. All of it held by gravity, the entire blanket of air weighing down on the surface. That's actually what atmospheric pressure is, the weight of all the air above you pressing down. At sea level, the atmosphere presses down on you with a force of about 10 newtons per square centimeter, or about 14.7 pounds per square inch in older units. You don't notice it. Your body has evolved to exist under exactly this pressure. Everything inside you pushes outward with the same force. It's perfectly balanced, but it's there. Gravity holding all of that air, pressing gently but firmly on every surface. On your skin right now, on the ground, on the ocean, a constant invisible weight. Let's think about something that might seem at first glance to contradict gravity. Orbits. The moon orbits the Earth. Satellites orbit the Earth. The International Space Station orbits the Earth. These things are up there, circling around, apparently not falling. So has gravity stopped working? Not at all. Everything in orbit is falling, constantly, continuously falling. Here's the key insight. If you throw a ball horizontally, it falls in a curve, pulled down by gravity, while also moving forward. The harder you throw it, the farther it travels before hitting the ground. Now imagine throwing the ball so hard that the ground curves away beneath it as fast as it falls. The ball is falling, always falling, but the Earth keeps curving away, and the ball never actually reaches the ground. It goes into orbit. This is exactly what an orbiting satellite is doing. It's falling toward Earth constantly, but it's also moving sideways so fast that it keeps missing. Earth curves away beneath it over and over in a continuous circle. The International Space Station, for example, travels at about 7.7 kilometers per second. That's roughly 28,000 kilometers per hour. At that speed, moving sideways, while the Earth curves away below, it maintains its orbit. It completes a full circle of the Earth in about 90 minutes. The astronauts aboard the space station feel weightless, not because gravity has stopped. Gravity is still very much present. At the space station's altitude, about 400 kilometers up, gravity is about 90% as strong as it is on the surface. The weightlessness comes from the fact that both the astronauts and the station are falling together at the same rate. There's nothing pressing against them, no floor pushing up on their feet, so they float. It's a peculiar, beautiful situation, falling and falling and falling, but never landing. Always curving around the Earth, always in free fall, but always in orbit. The moon does the same thing, just much farther away and much more slowly. It takes the moon about 27 days to complete one orbit. And Earth itself does the same thing around the sun. Earth is in free fall around the sun, constantly falling, constantly missing, completing one orbit every 365 days. The planets, the moons, the asteroids, all of them orbiting, all of them in free fall. all of them shaped and guided by gravity. We mentioned earlier that gravity weakens with distance according to what's called an inverse square law. Let's come back to this idea for a moment because it's quietly beautiful. If you double the distance from a massive object, the gravitational force drops to 1/4. Not 1/2, 1/4. If you triple the distance, it drops to 1/9. If you quadruple the distance, 1/16. This means that gravity falls off relatively quickly with distance, but it never reaches zero. Not in Newton's description, anyway. The Earth's gravity reaches out past the Moon, past Mars, past Jupiter. It gets very weak, but it's always there. In fact, the Milky Way's gravity reaches across the entire galaxy. And even beyond, the gravitational influence of our galaxy is felt by neighboring galaxies. In a real sense, every object in the universe is gravitationally connected to every other object. Pulling, barely pulling in most cases, almost unimaginably weakly, but always pulling. There is something quietly profound about this. You lying there are gravitationally connected to every star in the night sky. Your gravitational influence, tiny, almost completely negligible, reaches out across light years of space. And the gravity of those distant stars reaches back to you. Invisibly, silently, always. The universe is not a collection of separate, isolated objects. It's a web of gravitational relationships connecting everything to everything else. Always pulling, always reaching. Let's drift into a darker, deeper subject for a moment. Black holes. Black holes are one of the strangest things gravity produces, and yet they arise naturally, inevitably from the same simple idea. Mass creates gravity. A black hole is a region of space where gravity is so strong that nothing can escape, not matter, not light, nothing. They form when a very massive object collapses under its own gravity. The most common way this happens is at the end of a massive star's life. A star spends most of its life in a careful balance. The nuclear reactions in its core push outward, creating enormous pressure. Gravity pulls inward, trying to compress the star. These two forces balance each other. But when the star runs out of fuel, when the nuclear reactions stop, there's nothing to push back against gravity. And gravity wins. The star collapses inward extremely rapidly. For a star massive enough, this collapse is so extreme that the core is compressed into a point of infinite density, what physicists call a singularity. Around this singularity forms an invisible boundary called the event horizon. Inside the event horizon, gravity is so strong that escape velocity exceeds the speed of light. And since nothing can travel faster than light, nothing can escape. Not light, not information, nothing. The event horizon is not a physical surface. You can't touch it or see it. It's just a boundary, a line beyond which return is impossible. If you were to fall into a black hole from a comfortable, safe distance, this is entirely theoretical. You would feel nothing special at the moment you crossed the event horizon. No jolt, no wall, just space. But space you can never leave. From the outside, however, something interesting happens. Because of the way gravity bends time, which Einstein predicted, time near a black hole runs differently than time far away. This is called gravitational time dilation. Near a very strong gravitational field, time runs more slowly. If you were watching someone fall toward a black hole, you would see them slow down as they approached the event horizon. They would appear to slow and almost freeze, the light from them becoming dimmer and redder as it struggled against the gravity to reach you. From their perspective, they would cross the event horizon normally, but to you they would appear to never quite reach it. Black holes are in a sense the extreme end of what gravity can do, the most intense expression of the principle. that mass curves space-time. They sound frightening, and in science fiction, they often are. But from a comfortable distance, they're simply objects. Massive extreme, but following the same rules as everything else. The same rules that keep you resting on the Earth right now. In 2015, something remarkable happened. For the first time in human history, scientists directly detected gravitational waves. Gravitational waves are ripples in the fabric of space-time itself. They were predicted by Einstein in 1916 as a consequence of his general theory of relativity. But for nearly 100 years, they were purely theoretical. The idea is this: when massive objects accelerate, when they change their speed or direction, they can create ripples in space-time. Like a boat moving through water, leaving waves behind it. These ripples travel outward at the speed of light. They stretch and compress space itself very slightly as they pass through. The problem is that gravitational waves are extraordinarily weak. Even waves from the most violent events in the universe, two black holes colliding, by the time they reach Earth, they stretch and compress space by less than 1,000th of the diameter of a proton. That is an almost unimaginably small effect. It's not surprising it took so long to detect. The detection was made by an instrument called LIGO, the Laser Interferometer. Gravitational Wave Observatory. LIGO uses beams of laser light to detect the incredibly tiny stretching and compressing of space as a gravitational wave passes through. On September 14, 2015, LIGO detected a signal, a ripple in spacetime. The signal had been traveling for about 1.3 billion years. It was produced when two black holes, each roughly 30 times the mass of the Sun, spiraled toward each other and merged in an enormous collision. In the final moments of that collision, the event released more power than all the stars in the observable universe combined for a fraction of a second. And a tiny faint echo of that event, a whisper of rippling spacetime, reached Earth 1.3 billion years later. And we heard it. It's a quietly extraordinary achievement. Detecting something so faint, something predicted a century before. Ripples from a billion-year-old cosmic collision, stretching the fabric of space by less than a proton's width, and measuring it. Since then, many more gravitational wave events have been detected. Two neutron stars colliding, more black holes merging, each one a faint echo of ancient violence arriving at last as the softest possible, trembling in the geometry of space. Let's pause again. Breathe. We've come quite a long way now together. We started with the simple feeling of weight. We moved through Newton's laws, through the layers of the Earth, through Einstein's curved spacetime. We visited tides and orbits and black holes and gravitational waves. All of it, is the story of one simple thing. Mass creates gravity. Gravity shapes the universe. The floor beneath you, the air around you, the moon above you, the tides in the distant ocean, the orbits of planets, the waves in spacetime itself, all expressions of the same fundamental quality of the universe. There's something deeply peaceful about that. If you let yourself feel it, everything connected, everything pulling gently toward everything else, a universal web of quiet influence. Rest with that for a moment. Let's talk about the moon for a little while. The moon is about a quarter the size of Earth and has about 1/80th of Earth's mass. That means its surface gravity is about 1/6 as strong as Earth's. If you were standing on the moon, you would weigh about 1/6 of what you weigh on Earth. Every step you took would feel light bouncy. The Apollo astronauts walking on the moon in the 1960s and 1970s reported this clearly. Moving around felt different. Things fell more slowly. You could jump much higher. But the moon's gravity was still enough to make you feel grounded, to give you weight, to make you aware of up and down. The moon has no liquid water on its surface today, But it does have something interesting. Because its gravity is weaker, the moon cannot hold a substantial atmosphere. Gas molecules moving at normal speeds can exceed the moon's escape velocity and drift away into space. This is why the moon has essentially no atmosphere. Not because there was never any gas there, but because the moon's gravity is simply not strong enough to hold it. Earth, being larger and more massive, has escape velocity high enough to hold an atmosphere. Mars, being smaller, has a much thinner atmosphere. Its gravity is weaker, and much of its original atmosphere has been lost to space over billions of years. The size of a planet, and therefore the strength of its gravity, is one of the key factors in whether it can maintain an atmosphere. And without an atmosphere, life, as we know it, becomes very difficult. We're fortunate that Earth has just the right amount of mass, enough to hold an atmosphere thick enough to breathe, enough to maintain liquid water, enough to provide the steady, familiar pull that makes life possible. Speaking of escape velocity, let's sit with that idea for a moment. Escape velocity is the speed something needs to reach in order to escape from a planet's gravitational pull. For Earth, the escape velocity is about 11.2 kilometers per second. That's roughly 40,000 kilometers per hour. If you throw something upward at exactly that speed, in a vacuum, with nothing slowing it down, it will keep moving away from Earth indefinitely, gradually slowing, but never quite stopping, never falling back. At any speed slower than that, the object will eventually slow to a stop and fall back. At escape velocity, or above, it will escape entirely. The rockets that have sent spacecraft to the moon, to Mars, to the outer planets, they had to reach or exceed Earth's escape velocity. This takes an enormous amount of energy, burning huge quantities of fuel, to accelerate a relatively small payload to 11 kilometers per second. For the moon, escape velocity is only about 2.4 kilometers per second. That's why it's relatively easier, in energy terms, to launch from the moon than from Earth. Future plans for missions to Mars sometimes involve using the moon as a staging ground, partly for this reason. For a black hole, the escape velocity at the event horizon is exactly the speed of light. Nothing can go that fast, therefore nothing can escape. For the Sun, escape velocity at the surface is about 617 kilometers per second. The universe has a kind of escape velocity, too. Cosmologists talk about whether the universe is expanding fast enough to escape its own gravity forever, or whether gravity will eventually win and pull everything back. This is actually a deep, open question in cosmology. The fate of the universe, whether it expands forever, or eventually slows, stops, and perhaps contracts again. The answer depends on exactly how much mass the universe contains. And some of that mass, perhaps most of it, is invisible. We call it dark matter, but we'll come to that in a little while. Let's think about what it actually feels like to be in microgravity. Astronauts in orbit experience what's commonly called weightlessness or microgravity. As we discussed, they're not actually free of gravity, they're in free fall. But the effect is the same. They float. Living in microgravity is deeply strange, astronauts report. Everything floats. Water floats in blobs. Food floats. Tools float. Your arms don't hang at your sides. They drift forward, slightly following their own natural buoyancy. Sleep is different. Without gravity pressing you against a mattress, you don't feel the familiar heaviness of lying down. Astronauts sleep in sleeping bags tethered to the wall. The body adapts in interesting ways. Without gravity compressing the spine, astronauts actually grow slightly taller in space, up to a few centimeters. When they return to Earth, the spine gradually compresses again. Fluids in the body don't drain downward the same way. On Earth, fluids tend to pool in the lower body, and the brain compensates for this. In microgravity, fluids shift toward the upper body and head. Many astronauts report a feeling of congestion, a fullness in the face for the first few days as the body adjusts. Bones and muscles weaken in microgravity. On Earth, gravity provides a constant low-level workout. Your muscles and bones are always working against it. In space, without that constant resistance, they begin to weaken. Astronauts must exercise for roughly 2 hours every day to counteract this. Long-duration missions, 6 months a year, lead to significant bone density loss and muscle atrophy. Returning astronauts sometimes need to be carried from their spacecraft. Their bodies adapted to weightlessness find Earth's gravity suddenly heavy and difficult. It takes weeks, sometimes months, to readapt. This tells us something important. Our bodies are shaped by Earth's gravity, not just metaphorically, physically, literally. Our bones are the density they are because of gravity. Our muscles are structured the way they are because of gravity. Our cardiovascular system is arranged partly in response to gravity. Gravity has shaped every organism that has ever evolved on Earth. Over 4 billion years. Every cell, every system, every structure, all quietly organized in response to the steady patient pull of the Earth. That brings us to something worth lingering on for a while. The relationship between life and gravity. Life on Earth evolved in the presence of Earth's gravity. There has never been a moment in the history of life on this planet when gravity was absent. Not once, not even briefly. This means gravity is baked into the very structure of life, into the shape of every living thing. Think about trees for a moment. Trees grow upward against gravity. Their roots grow downward following it. Specialized cells in the root tips sense gravity directly. They contain small, dense particles called statoliths that sink to the bottom of the cell under gravity, telling the root which way is down. Animals have evolved vestibular systems, organs in the inner ear that sense gravity and acceleration. That small spiral structure in your ear, the cochlea, and its neighbors contains tiny calcium crystals similar in a way to the plant statoliths that move under gravity and tell your brain which way is up. This is how you know which direction you're oriented. Even with your eyes closed, you generally know if you're upright or lying down. That's your inner ear detecting gravity. Organisms that live in environments where gravity is partially offset, like marine creatures floating in water, have different structural adaptations. They don't need to carry as much skeletal support because buoyancy takes over some of gravity's load. Land animals, moving in air, need much stronger skeletons. The skeleton is essentially an infrastructure built to resist gravity, to hold the organism upright, to allow movement against the constant downward pull. The tallest land animal that has ever lived, probably a sauropod dinosaur, was likely near the upper limit of what bone can support under Earth's gravity. Even larger, and the skeleton wouldn't hold. The blue whale, the largest animals alive today, can be so large, partly because they live in water. Their weight is supported by buoyancy. A blue whale on land would be crushed under its own weight, its internal organs compressed, unable to breathe. Gravity sets the scale for life. It determines how big things can be, how they must be structured, how they move. Every living thing on Earth is a solution to the problem of gravity. A beautifully, elegantly evolved solution. One of gravity's most visible daily effects on Earth's surface is the way it shapes the movement of water. Water flows downhill. That simple phrase contains all of gravity's relationship with water. Water flows to lower elevations following gravity, always seeking the lowest point available. Rivers are rivers because of gravity. A river is simply water flowing along the path of least resistance toward lower and lower ground pulled along by gravity until it reaches the ocean, the lowest point on the surface. The ocean itself sits in low-lying basins collected there by billions of years of gravity-driven flow. Rain falls because of gravity. Clouds form in the atmosphere, water droplets condense, and when the droplets are heavy enough, gravity pulls them down as rain. Waterfalls are gravity in its most theatrical form. Water moving horizontally off a cliff edge, and then suddenly falling pulled straight down. The Niagara Falls, the Angel Falls, the Victoria Falls, all the same simple idea. Gravity and water with nowhere horizontal left to go. Groundwater, water that seeps into the soil and rock beneath the surface, also moves under gravity. It percolates downward through permeable rock, collecting in underground aquifers. When wells are drilled down to these aquifers, gravity helps bring the water up. Or sometimes the pressure of surrounding rock forces it upward, creating artesian wells that flow without pumping. Even the water cycle, the great circulation of water through evaporation, cloud formation, rain, rivers, and ocean, is fundamentally driven by two forces working together. Sunlight provides the energy to evaporate water and lift it into the atmosphere. Gravity provides the constant pull that brings it back down. Over and over, endlessly cycling. Water, lifted by the sun, returned by gravity. It's a very old cycle. Water has been cycling like this on Earth for at least 4 billion years. The water in your body tonight has been through that cycle countless times. Has been rain, has been river, has been ocean, has been cloud, over and over, pulled down by gravity, lifted by sunlight, pulled down again. The surface of the Earth is not flat. It's full of ridges and valleys, peaks and plains, and gravity played a significant role in shaping all of these. Mountains form when tectonic plates collide, or when volcanic material pushes up through the crust. Gravity constantly works against mountains, trying to wear them down. Erosion, the slow wearing away of rock and soil by water, wind, and ice, is primarily powered by gravity. Rain falls on the mountain and flows downhill, carrying small particles of rock with it over millions of years. This removes the mountain, piece by piece. The Appalachian Mountains in eastern North America are ancient, over 300 million years old. They were once as high as the Himalayas, but hundreds of millions of years of erosion, driven by gravity, have worn them down to gentle, rounded hills. The Himalayas are younger and still actively rising. The Indian tectonic plate is still slowly colliding with the Eurasian plate, pushing rock upward faster than erosion can remove it. For now, eventually, the collision will slow. Erosion, gravity's patient work, will catch up. The Himalayas, too, will be worn to gentle hills, given enough time. Valleys form where rivers have carved into rock over millions of years. The Grand Canyon is a valley carved by the Colorado River over 5 million years. Gravity-driven water has cut through layer after layer of rock. Glaciers also carve valleys, huge rivers of ice, moving slowly, under their own weight, under gravity, scraping and grinding rock, creating the characteristic U-shaped valleys you find in mountain regions. The shape of the land beneath you is in large part the accumulated record of gravity's patient, persistent work over millions and millions of years, pulling water downhill, pulling ice down slopes, pulling rock and soil toward the sea. The landscape is gravity made visible. Let's move into slightly more mysterious territory. Gently, when astronomers observe galaxies, enormous collections of stars, gas, and dust held together by gravity, they find something puzzling. the galaxies don't move the way they should, given the amount of visible matter they contain. Stars in the outer regions of galaxies orbit faster than they should, based on the gravity we can calculate from the visible stars and gas. This was first noticed clearly by an astronomer named Vera Rubin. In the 1970s, she measured the speeds of stars at different distances from the center of galaxies. If gravity came only from the visible matter, stars far from the center should move more slowly, as planets far from the sun do. But they didn't. They moved just as fast, or even faster, than stars near the center. The only explanation that fits is that there's additional mass in these galaxies, mass that we can't see. This invisible mass is called dark matter. We don't know exactly what dark matter is. It doesn't emit light. It doesn't absorb light. It doesn't interact with the electromagnetic force that governs most of what we experience. It only interacts through gravity. And yet, it must be there. The gravitational evidence is overwhelming. Astronomers estimate that dark matter makes up about 27% of the total energy content of the universe. All the visible matter, all the stars, all the galaxies, all the planets, all the gas, makes up only about 5%. There's also something called dark energy, a mysterious force that seems to be driving the expansion of the universe. To accelerate, dark energy is estimated to make up about 68% of the universe. So in a sense, what we can see and understand directly is only a small fraction of everything that exists. Most of the universe is dark matter, interacting only through gravity, dark energy, pushing the universe apart. These are open mysteries, active areas of research. We don't know what dark matter particles are. We don't know what dark energy is. But gravity, the same gravity that holds you to the Earth, is the force that has revealed their existence. By watching how things move, how galaxies spin, how light bends around massive objects, we can infer the presence of invisible mass. Gravity, in a sense, is our window into the dark universe. Let's return to orbits for a little while and look at them more carefully. Orbits are not always circles. They can be ellipses, elongated ovals of various degrees. Johannes Kepler, a German mathematician who lived in the early 1600s, worked this out. He spent years analyzing careful astronomical observations made by the Danish astronomer Tycho Brahe, and he discovered that the planets move in ellipses, not circles. Kepler worked this out before Isaac Newton explained why. Kepler described the shapes of the orbits. Newton explained the force behind them. An ellipse has two focal points. In a planetary orbit, the Sun is at one of those focal points. This means that a planet is not always the same distance from the Sun. At some points in its orbit, it's closer. At other points, farther. For Earth, the closest point to the Sun in our orbit is called perihelion. We reach perihelion in early January, slightly counterintuitively, in the middle of northern winter. The difference in distance isn't large enough to significantly affect seasons. Seasons are caused by Earth's axial tilt, not its distance from the Sun. The farthest point is called aphelion, reached in early July. The difference in distance between perihelion and aphelion is only about 5 million kilometers. Not huge, compared to our average distance of about 150 million kilometers from the Sun. Some objects have much more elongated orbits. Halley's Comet, for example, has a highly elliptical orbit. At its closest, It comes inside the orbit of Venus. At its farthest, it goes beyond the orbit of Neptune. Kepler also discovered something elegant. A planet moves faster when it's closer to the sun and slower when it's farther away. This makes sense from an energy perspective and from Newton's gravity too, since the sun's gravitational pull is stronger at closer distances. This is why Earth is moving slightly faster through space in January than in July, closer to the sun, pulled more strongly, moving faster. We don't feel any of this variation. Our orbit is smooth enough, our speed varies gently enough, that there's no sensation of it. We just circle on, year after year, in our quiet ellipse. The sun is the dominant gravitational presence in our solar system. Let's think about it for a moment. The sun contains about 99.86% of all the mass in the solar system. All the planets together, Jupiter, Saturn, all of them, make up less than 0.15%. Earth's contribution is almost infinitesimal. The sun's surface gravity is about 28 times stronger than Earth's. If you could stand on the sun, which you cannot, but imagining it gently, you would weigh 28 times more than you do on Earth. The sun's escape velocity, as we mentioned, is about 617 kilometers per second. The sun's gravity controls the orbits of all the planets. Mercury, closest to the sun, moves the fastest in its orbit, about 47 kilometers per second. Neptune, the farthest major planet, moves much more slowly, about 5 kilometers per second. The sun's gravity even holds distant objects. The Oort cloud, a vast spherical shell of icy bodies thought to orbit the sun at distances of tens of thousands of astronomical units, is still gravitationally bound to the sun, though just barely. The sun itself is in motion. Our solar system orbits around the center of the Milky Way galaxy. We're located roughly 26,000 light years from the galactic center, and we complete one orbit around the galactic center every 225 to 250 million years. This is sometimes called the galactic year or the cosmic year. In the 4.5 billion year history of the solar system, we have completed about 18 to 20 orbits around the galactic center. The galaxy, in turn, is part of a larger structure, the local group, a cluster of about 50 galaxies bound together by gravity. The Milky Way and the Andromeda Galaxy are the two largest members, and the local group is itself part of the Virgo supercluster, and that is part of the Laniakea supercluster, an enormous gravitational structure containing hundreds of thousands of galaxies spanning about 520 million light years. Gravity operating at every scale, from the atoms in your body to the largest structures in the observable universe. The same force, the same principle. Mass creates gravity. Gravity shapes everything. This might seem like an odd section. What does gravity sound like? Gravity itself doesn't produce sound. Sound requires a medium, air, water, some physical substance, for the pressure waves to travel through. Gravity, working in the vacuum of space, is silent, but the effects of gravity can produce sound. The sound of rain is the sound of water pulled down by gravity. The low, deep roar of a waterfall is gravity-driven water falling. The sound of that energy releasing. The sound of wind, in a sense, is air moving from high pressure to low pressure, driven partly by temperature differences created by the sun, but flowing downward in pressure gradients that are themselves influenced by gravity. the ocean waves crashing on a shore, have their sound partly from gravity. The wave rises, crests, and then gravity pulls the water down and forward, that collapsing weight producing the rushing, rumbling sound of surf, thunder, the sound of air rapidly heated and expanding from a lightning bolt. The storm itself is partly driven by convection, the rising and falling of air under gravity's influence. Even the ground settling at night, the small creaks and shifts of a building are, in a sense, gravity's voice, material adjusting slightly under constant gravitational load, finding a more settled position. Gravity is all around us, in sound, in rain and rivers, in waves and wind, in the settling of buildings, and the distant rumble of thunder. As you lie there, listen, if there's any sound at all, where you are, even the faintest creak of the building, even the distant sound of rain, some of that sound is gravity. Some of that sound is the Earth's pull, expressed as motion, expressed as pressure, expressed as vibration in the air. The Earth, always gently, speaking. Before Isaac Newton, before Galileo Galilei, people had various ideas about why things fall. Let's look at them gently, with no judgment. These were thoughtful people, doing their best with what they had. The ancient Greek philosopher, Aristotle, who lived in the 4th century BC, had an elegant, but ultimately incorrect, explanation. He believed that the elements, earth, water, air, and fire, each had a natural place. In the cosmos, earth and water naturally sought the center of the universe, which in his model was the center of the earth. Air and fire naturally rose. So things fell to earth, not because of a force, but because material made of earth and water was seeking its natural home. This made a certain poetic sense, and it fit everyday observation well enough that it wasn't seriously challenged. For nearly 2,000 years, Aristotle also believed that heavier objects fell faster than lighter ones. This also seemed like common sense. A rock falls faster than a feather, but as Galileo Galilei showed, that's because of air resistance, not gravity. In a vacuum, they fall at the same rate. The Indian mathematician and astronomer Brahmagupta, in the 7th century CE, wrote that heavy and light objects fall to the earth at the same speed. This was a remarkable early observation, made nearly 1,000 years before Galileo Galilei. In medieval Islamic astronomy, scholars like Ibn Sina made careful observations of celestial mechanics. They grappled with questions about force and motion that would eventually lead, through many generations of thought, toward Isaac Newton. Each of these thinkers was building on those before them, each getting a little closer to the understanding we have today. It's worth remembering that the story of science is not a story of sudden insight. It's a story of gradual refinement, patient observation, careful thinking, slow progress, each generation adding a small piece. Isaac Newton himself said, famously, that he was standing on the shoulders of giants. He meant it genuinely. His own synthesis was brilliant, but it was built on the work of Nicholas Copernicus, Johannes Kepler, Galileo Galilei, and countless others. And our current understanding, shaped by Albert Einstein and many others, is built on Newton's work. The story continues. We don't yet have a complete theory of quantum gravity, a single framework that unifies Einstein's general relativity with quantum mechanics. That remains an open challenge. The next giant shoulders are not yet fully formed, but they will be. There's a specific experience of gravity that's worth noticing. the feeling of landing. When you jump, even slightly, stepping off a small ledge, there's a brief moment of weightlessness. Your feet are not in contact with the ground. You're in free fall. For a fraction of a second, you experience something like what astronauts experience. No normal force pushing up on your feet, just your body and gravity. And then you land. Contact, impact, weight returns. The ground pushes up against your feet, your legs, your whole body. You're no longer in free fall. That moment of landing, that return of weight, is in a small way the same moment that defines a spacecraft re-entering the atmosphere of the Earth, or the same moment that defined the Apollo program capsules splashing down into the ocean. Free fall, then contact, weightlessness, then weight. The body knows it well. It's one of the most ancient sensations living things have. The return to Earth, the solid ground, the familiar pull, reasserting itself. Even birds, after a flight, land, after soaring, on thermal currents, air rising, under the warmth of the sun, given direction by gravity. They come down, they land. Gravity, always patient, always present, waits, and eventually, everything returns to it. The leaf falls, the raindrop falls, the tired bird lands. And you, right now, are perfectly, completely, in gravity's embrace, resting, settled, held. We touched on this earlier, but let's return to it and move through it more slowly. The formation of the solar system, because it's a story that really belongs entirely to gravity. About 4.6 billion years ago, there was no solar system. There was a large cloud of gas and dust, what astronomers call a nebula, drifting in the Milky Way. Something disturbed this cloud, perhaps the shockwave from a nearby supernova, perhaps the gravitational influence of a passing star. Whatever the cause, the cloud began to collapse, slowly at first, then faster. As the cloud collapsed, gravity pulled more and more gas toward the center. The center grew denser, hotter, gas molecules compressing together, releasing heat. Eventually, the core became hot and dense enough that nuclear fusion began. Hydrogen atoms began fusing together to form helium, releasing enormous amounts of energy. The sun ignited around the young sun. The remaining gas and dust formed a rotating disk. This disk is called the protoplanetary disk. Within this disk, gravity was at work. Again, particles of dust and ice began to stick together. Small clumps formed. Small clumps drew in more particles, grew into larger clumps. These planetesimals, small bodies in the early solar system, continued to collide and merge. The ones that happened to be in similar orbits would eventually merge into larger bodies close to the sun. The temperature was too hot for ice to exist. Only rock and metal, high-temperature materials, could condense there. So the inner planets, Mercury, Venus, Earth, Mars, are rocky. Farther out, beyond a region called the frost line, water ice could exist. Ice dramatically increased the amount of material available for planet formation. Jupiter and Saturn grew quickly and massively, accumulating enormous quantities of ice and gas. They grew so large that their gravity was strong enough to pull in hydrogen and helium directly from the surrounding gas. These became the gas giants. Even farther out, Uranus and Neptune formed ice giants containing large amounts of water, ammonia, and methane ice, in addition to gas. The process took millions of years, and at the end of it, 8 major planets and countless smaller bodies circled the young sun. All of it organized, separated, sorted by gravity. The inner rocky planets, the asteroid belt, the outer gas giants, the Kuiper belt of icy bodies, the distant Oort cloud, each zone reflecting the conditions of that early disk and the sorting action of gravity. Our solar system is, in a deep sense, a fossil of gravity, a record of how mass accumulates, collapses, and organizes itself under its own pull. Stars are gravity's great projects. A star is, in essence, a balance between gravity and pressure. Gravity pulls inward, trying to compress the gas. Pressure pushes outward, resisting compression. For most of a star's life, these two forces are in almost perfect balance. It's called hydrostatic equilibrium. The same phrase, you may remember, that describes why planets are round. For the Sun, this balance has been maintained for 0.6 billion years. It will continue for another approximately 5 billion years. During this time, the Sun is quietly converting hydrogen to helium in its core. About 620 million tons of hydrogen per second. This releases energy, which creates the outward pressure that balances gravity. When the hydrogen in the core is exhausted, the balance will change. The core will contract under gravity, growing hotter. The outer layers will expand, cooled, and puffed outward by the increased energy flow. The Sun will become a red giant, large enough in that distant future to swallow the inner planets. Eventually, the outer layers will drift away. The core will be left as a white dwarf, a dense, cooling remnant about the size of the Earth, but with roughly half the mass of the Sun. No more fusion, just slowly cooling over billions and billions of years. For more massive stars, the end is more dramatic. A star, several times the mass of the Sun, will eventually detonate in a supernova, an explosion visible across galaxies, leaving behind either a neutron star or a black hole. A neutron star is extraordinary. It's the collapsed core of a massive star, so dense that a teaspoon of neutron star material would weigh about 1 billion tons. The entire object is roughly 20 kilometers across, about the size of a city, but contains more mass than the Sun. Gravity has compressed the material so completely that the electrons and protons have merged to form neutrons, a solid ball of neutrons packed as tightly as the nucleus of an atom. The surface gravity of a neutron star is roughly 100 billion times stronger than Earth's. If you were somehow standing on the surface of a neutron star, you would be instantly and completely flattened. Your entire body would be squeezed into a layer thinner than an atom. Gravity is a gentle, familiar friend here on Earth, but at the extremes of the universe, it is the most fearsome force imaginable. The architect of both stars and their spectacular endings. We touched on this earlier, but it's worth exploring more fully. Gravity affects time. This is one of Albert Einstein's most astonishing predictions. In a strong gravitational field, time runs more slowly. This effect is called gravitational time dilation. It's been measured, very precisely. GPS satellites orbit about 20,000 kilometers above the surface of the Earth. At that altitude, they experience slightly weaker gravity than we do at the surface, and because of gravitational time dilation, clocks on GPS satellites run slightly faster than clocks on the ground. Additionally, the satellites are moving fast, and according to special relativity, moving clocks run slightly slow. Both of these effects have to be corrected for. The global positioning system explicitly accounts for the predictions of both special relativity and general relativity. If it didn't, the positional errors would accumulate at a rate of several kilometers per day. So every time you use GPS on your phone, in your car, you're benefiting from Albert Einstein's theories of curved spacetime, of time dilation, of gravity's effect on clocks. The effect is small at everyday scales. The GPS correction amounts to only microseconds per day, but it's real, measurable, and must be accounted for. Near a neutron star, the time dilation would be enormous. Time close to a neutron star's surface would pass significantly more slowly than time far away. An hour near the surface might correspond to years farther away. And near a black hole's event horizon, as we mentioned, time dilation approaches infinity. Clocks near the event horizon appear from the outside to slow to a complete stop. Time is not a fixed, universal constant. It flows differently, depending on gravity. Right now, your head is slightly farther from Earth's center than your feet are. The gravitational field is very slightly weaker at your head than at your feet, and time runs very, very slightly faster at your head than at your feet. The difference is extraordinarily small, but it's real. In 2010, physicists at the National Institute of Standards and Technology demonstrated gravitational time dilation at a height difference of just 33 centimeters using atomic clocks so precise that they could measure this tiny difference. Even lying down, head and feet level, you experience the universe in this faintly different way. Time and gravity, always intertwined. Let's drift gently to a quieter subject, the ocean floor. The ocean floor is one of the least explored places on the Earth. Vast, dark, cold, and distant from the surface, and it lies where it does, entirely because of gravity. The ocean basins are lower than the continental land masses, partly because the oceanic crust is denser and thinner than continental crust, sitting lower in the mantle, and so water, flowing to the lowest available point, following gravity, has filled these basins. The deepest point on Earth's surface is the Mariana Trench in the Pacific Ocean. It reaches nearly 11 kilometers below sea level. At that depth, the pressure is enormous, about 1,100 times atmospheric pressure. At the surface, this pressure is the weight of all the water above, pressing down, the weight of all that water held by gravity, compressing the water below. And yet, even there, life exists. Strange, patient creatures, living in the cold and dark, under enormous pressure. The deep ocean was thought to be lifeless for a long time, but it isn't. Bacteria, tube worms, palefish, strange crustaceans, life adapting to conditions of almost unimaginable pressure and cold. Gravity keeps the water there. Gravity keeps the pressure there. And in that dark, pressurized world, shaped by gravity, life found a way. As it always does, there's a beautiful, quiet piece of science worth mentioning here. A number called the Chandrasekhar limit. Subramanian Chandrasekhar was an Indian astrophysicist who in 1930 calculated the maximum mass that a white dwarf star can have. He was 19 years old. At the time, he worked it out on a ship crossing from India to United Kingdom. The limit is about 1.4 times the mass of the Sun. Below this limit, a white dwarf is stable. The outward pressure of its electron to generate matter, a quantum mechanics effect, can resist gravity. Above this limit, gravity wins. The white dwarf will collapse further. If the star was not too much heavier, it collapses to a neutron star. If it was very massive, it collapses to a black hole. The Chandrasekhar limit turns out to be cosmologically important. Type Ia supernova, a particular kind of stellar explosion, happen when a white dwarf reaches this limit by accumulating mass from a companion star. Because the explosion always happens at exactly the same mass, the Chandrasekhar limit, these supernovae always have almost exactly the same brightness. This makes them useful as standard candles, objects whose true brightness is known, allowing astronomers to measure how far away they are by how bright they appear. Type Ia supernova have been used to measure the expansion of the universe, and it was through these measurements in the late 1990s that astronomers discovered that the expansion of the universe is accelerating, which led to the concept of dark energy, all because one young man on a ship worked out what gravity could and couldn't do to the matter inside a dying star. A beautiful chain of insight, the Chandrasekhar limit, connecting a 19-year-old's calculation to the fate of the universe. On different worlds, gravity is different, and this affects everything, including how high mountains can be. On a world with stronger gravity, the crust is crushed down more firmly. It's harder for tall structures to exist. The maximum height of a mountain is limited by the strength of rock relative to the gravitational pressure. Trying to compress it on a world with stronger gravity, mountains tend to be shorter. On a world with weaker gravity, mountains can be taller. Mars has weaker gravity than the Earth, about 38% as strong, and Mars has the tallest known volcano in the solar system, Olympus Mons. Olympus Mons is about 22 kilometers high, nearly 3 times the height of Mount Everest. It could be that tall, partly because Mars's weaker gravity allows taller structures without the crust collapsing under the weight. On the Earth, Mount Everest is about 8.8 kilometers above sea level. This is near the practical maximum for Earth's geology and gravity. If the Himalayas pushed up any higher, the rock at the base would begin to flow under the enormous pressure. Isostasy, the adjustment of the crust under gravitational load, would pull the mountain back down. Neutron stars, with their ferocious gravity, have essentially no surface features. Mountains on a neutron star can be no more than a few millimeters high before they're crushed flat by gravity. The tallest mountain, the flattest surface, all determined by the balance between the strength of material and the pull of gravity. on every world. The same principle, just different numbers. Let's sit for a moment with something simpler. You exist right now, reading or listening to these words. You exist, and you exist here, on this particular Earth, with this particular gravity. The conditions that allow you to exist are astonishingly specific. A planet, the right size to hold, an atmosphere, the right distance from the right kind of star, with enough gravity to keep water liquid on the surface, with a moon just the right size to stabilize the axial tilt and drive the tides, with a large outer planet, Jupiter, whose gravity diverts many asteroids and comets away from the inner solar system. Each of these conditions involves gravity, the size of the planet, gravity, the orbit stability, gravity, the moon's presence and size, gravity, Jupiter's protective role, gravity. Life, as far as we know, requires very specific conditions, and many of those conditions are gravitational conditions. Whether this means Earth is unique or whether similar conditions exist throughout the Milky Way and beyond, we don't yet know. The search for other habitable worlds is ongoing. But here, right now, the conditions are met. The gravity is just right. The atmosphere is held in place. The water flows. The temperature is in range. And you're here, resting, held gently to the surface of a planet perfectly calibrated by chance and time to support your existence. There's something quiet and profound about that, if you let it in. We've talked a great deal about gravity pulling things together, but let's spend a moment on the other side of the story. The universe is expanding. In 1929, an astronomer named Edwin Hubble made a remarkable discovery. Distant galaxies are moving away from us, and the farther away the faster they're moving. This is called Hubble's law, and it means the universe is expanding. An expanding universe means that, in the past, everything was closer together. Wind back the clock far enough, and everything was in the same place. That initial moment is called the Big Bang. For the first billion years or so after the Big Bang, matter was more uniformly spread. Then gradually, slight overdensities, regions with a tiny bit more matter than average, began to grow. Gravity amplified these overdensities. Slightly denser regions pulled in material from their surroundings, became denser still, pulled in more material. Over hundreds of millions of years, these regions formed into the first stars and galaxies. The large-scale structure of the universe, the vast web of galaxy filaments and voids, is the end product of gravity amplifying the tiny density fluctuations that existed in the early universe. These initial density fluctuations are thought to trace back to quantum fluctuations in the very earliest moments of the universe. Quantum mechanics randomness expanded to cosmic scale, shaped by billions of years of gravitational amplification, into stars, into galaxies, into clusters of galaxies, into the universe we see today. All of this structure, everything we can see in the night sky, is gravity's artwork. Gravity organizing the products of the Big Bang into patterns and structures The universe began as nearly uniform. Gravity gave it texture, gave it variety, gave it stars and planets and the possibility of life. We've traveled very far tonight from the pull you feel in your body right now to the large-scale structure of the universe, from Isaac Newton's apple to Albert Einstein's curved spacetime, from the deepest ocean trenches to the formation of stars. But all of it circles back to the same simple idea. Mass creates gravity. Gravity shapes everything. The Earth you're lying on right now is a ball of rock and iron, billions of years old, accumulated under its own gravity from the debris of the early solar system. It has just enough mass to hold an atmosphere, just enough mass to pull the moon into orbit, just enough mass to drive the tides, just enough mass to keep water liquid on its surface. It curves space-time very slightly, gently, in a way that guides your body toward its surface. You feel that as weight, as the comfortable, familiar sensation of being grounded, of being here. Every object that has ever fallen, every apple, every raindrop, every leaf, every piece of dust has followed the curve that Earth makes in the fabric of space. You are doing the same right now, resting in that curve, held there by the accumulated mass of this ancient world. It's a very quiet thing. Gravity doesn't announce itself. It doesn't demand attention. It simply is always there, always the same. A constant, gentle presence. If you ever find yourself in a dark place, far from city lights, and you look up at the night sky, everything you see up there is moving, and almost everything is moving because of gravity. The stars you see are in slow orbits around the center of the Milky Way. Our own sun takes 225 million years to complete one orbit. The stars near us are moving in their own orbits at slightly different speeds and angles, creating a slow, majestic drift over millions of years. The planets you might see, the bright, steady lights that don't twinkle like stars, are moving in their elliptical orbits around the Sun, Jupiter, Venus, Mars, each following the curve of spacetime shaped by the Sun. The Milky Way itself, that pale band of light across the sky, is the combined light of hundreds of billions of stars, all in orbits around the galactic center. The galactic center contains a supermassive Sagittarius A*, with about 4 million times the mass of the Sun, orbiting galaxies. In the local group, the Andromeda Galaxy, the Magellanic Clouds are moving under the combined gravity of all the matter in the cluster. Andromeda Galaxy, in fact, is moving toward us in about 4.5 billion years. The Milky Way and the Andromeda Galaxy will collide and merge, a slow, immense collision, taking hundreds of millions of years. Stars won't collide, they're too far apart, but the galaxies will pass through each other, distorting and merging their stars, rearranging into a new, larger galaxy. All of this written in the night sky, all of it the story of gravity, the quiet, cold beauty of the stars. At night is the beauty of gravity, of mass, drawing mass together, of structure arising from the long, patient work of an invisible force. We've been together for a long time now, moving slowly through all of this. You've heard about the layers of the Earth, about the laws described by Isaac Newton, and the curved space-time of Albert Einstein, about tides and orbits and black holes and gravitational waves, about the formation of the solar system and the structure of stars, about life shaped by gravity and water guided by gravity and mountains limited by gravity. All of it comes back to the same quiet truth. Mass creates gravity. Gravity shapes the universe. And right now, in this moment, that means something specific and personal. It means the Earth is holding you with a force that has never wavered. Not once, not in the billions of years, this planet has existed. The same gravity that built this world from dust and rock is holding you right now. The same gravity that keeps the oceans in their basins and the air in the atmosphere is pressing you gently and firmly into whatever you're lying on. You don't have to do anything for this. You don't have to earn it. You don't have to maintain it. It's simply there. Gravity is perhaps the most unconditional thing in the universe. No matter who you are, no matter what you've done or haven't done, no matter what you're worried about or what you hope for, gravity holds you, always. Let that be a small comfort. If you can, the Earth, ancient and vast and endlessly patient, holding you right now, in this moment, as it always has, as it always will. Let's spend a little time with something very close to home. The ground itself, the rocks beneath your feet, beneath the thin layer of soil and concrete, and whatever else sits between you and the crust of the Earth are the product of gravity and time working together. Sedimentary rocks form when particles of sand, silt, and clay settle to the bottom of bodies of water. They settle because of gravity. Gravity pulls those tiny particles slowly downward through the water. They accumulate on the bottom, layer by layer. Over time, millions of years, those layers are buried by more layers. The weight of the new layers pressing down, compressing the old ones. Gradually, the particles are cemented together. Loose sediment becomes solid rock. The pressure that creates this rock is the weight of overlying material, which is to say, gravity. This is why sedimentary rock often has a layered appearance. The strata you see in cliff faces or canyon walls are the record of ancient deposits. Each layer, a moment in time. Each layer, created by gravity, pulling particles downward through ancient water. Some of the most beautiful scenery on the Earth, the layered colors of the Grand Canyon, the striped cliffs of Bryce Canyon, the gentle bands of color in the painted desert, are all books written in the language of gravity and time. Igneous rock forms differently. It comes from molten material, magma, rising from within the Earth. Magma is less dense than surrounding rock, so it rises. Less dense means it floats upward in a gravitational field, just as a bubble rises through water. When magma reaches the surface, it's called lava. When lava cools and solidifies, it becomes igneous rock. Basalt, the dark rock that forms much of the ocean floor, is igneous. Granite, the speckled stone used in buildings, is also igneous, formed deep underground, where magma cooled, slowly. Metamorphic rock forms when existing rock is subjected to heat and pressure. Again, pressure, and therefore, gravity, plays a central role. Deep in the crust, where layers of rock pile up overhead, the pressure is enormous. That pressure, combined with heat, can transform one rock into another. Limestone becomes marble, shale becomes slate, sandstone becomes quartzite. The entire rock cycle, the slow transformation of rock from one type to another over millions of years, is powered partly by gravity, particles settling, weight accumulating, pressure building, rock rising, cooling, eroding, settling. Again, the ground is in motion, always, just very, very slowly. Gravity is always reshaping it, patiently, persistently, over timescales, far beyond anything in human experience. The seasons are not caused by gravity directly, but gravity's role in creating them is worth understanding because it's a common misconception. Many people believe that the Earth is closer to the Sun in summer and farther in winter. This is not correct. In fact, the Earth is closest to the Sun in early January, in the middle of northern winter. The seasons are caused by the tilt of Earth's axis. Earth's axis is tilted about 23.5 degrees relative to the plane of its orbit around the Sun. For part of the year, the northern hemisphere is tilted toward the Sun. The Sun appears higher in the sky. Days are longer. Sunlight hits the ground more directly. This is northern summer. 6 months later, the northern hemisphere is tilted away from the Sun. The Sun appears lower. Days are shorter. Sunlight spreads over a larger area. This is northern winter. Gravity's role is indirect, but important. The orbit that carries the Earth around the Sun is shaped by the Sun's gravity, and the tilt that creates the seasons is stabilized by the Moon. The Moon's gravitational pull damps out large wobbles in Earth's axis, keeping the tilt relatively stable over long periods of time. Without the Moon, Earth's tilt might vary chaotically, swinging from nearly 0 degrees to more than 85 degrees over millions of years. Such extreme swings could produce dramatic climate changes that might make complex life much harder to develop. The Moon, pulled by the gravity of the Earth, helps keep our seasons predictable, our climate relatively stable. Meanwhile, Mars has no large moon to stabilize its tilt over millions of years. Its axial tilt has shifted dramatically from about 15 degrees to more than 35 degrees, changing its climate again and again. The Moon, quietly orbiting the Earth, stabilizing our world's tilt, helping create the gentle, predictable rhythm of seasons. Gravity, once again, working quietly in the background of everything. Let's come back to the human body and go a little deeper. Every system in your body has been shaped by the need to function in Earth's gravitational field, not just muscles and bones. Everything, the cardiovascular system, your heart and blood vessels, is organized partly around the challenge of pumping blood against gravity. Your heart pumps blood upward to your brain, which is the highest point of your body. When you're standing, this requires pressure. Your heart generates that pressure. With each beat, blood vessels in your legs have valves, small flaps, that prevent blood from falling back down toward the feet when it should be moving upward. Without these valves, blood would pool in the lower extremities. When you stand up quickly from lying down, sometimes you feel momentarily dizzy. That's your cardiovascular system briefly struggling to adjust blood pressure to maintain flow to the brain, gravity pulling blood downward faster than the vessels can compensate. It passes quickly as the body adjusts. The inner ear, as we mentioned, contains organs that detect gravity and acceleration. These are the utricle and the saccule, part of the vestibular system. They contain small crystals, called otoliths, ear stones, that press on hair cells when gravity or acceleration pulls them. This is how your brain knows which way is up, how it maintains your sense of balance, how it keeps you oriented in space. When the vestibular system is disrupted by illness, by unusual motion, the result is vertigo or motion sickness. The world seems to spin. You feel disoriented, nauseous. Your brain is receiving conflicting information about which way gravity is pointing. The digestive system also operates partly under gravity. Food moves down the esophagus, partly due to muscular action, peristalsis, but gravity assists in the stomach and intestines. The position of the body affects how contents move. We generally eat and sleep in orientations that work with gravity. Lying down to eat can lead to discomfort, in part because it changes the gravity-assisted movement of food. Even posture, the way you hold your body, is a constant negotiation with gravity. Standing upright requires a complex system of muscle contractions and skeletal positioning to resist gravity's downward pull. Good posture means the skeleton is arranged so that gravity's force passes cleanly through the body with minimal muscle effort. Poor posture means muscles are working harder to maintain an unstable configuration. The human body is, in a sense, a machine designed to operate in Earth's specific gravitational field. Not any field. This one, 9.8 meters per second. Your body is tuned to this, calibrated to it, over millions of years of evolution. When it's right, when you're on Earth, in Earth's gravity, everything runs smoothly. When it's different, in space, or even at high altitude, the body must adapt. You are, in a very deep sense, a creature of this planet's gravity. There's a curious and beautiful consequence of gravity, Lagrange points. When two massive bodies orbit each other, like the Earth and the Sun, their combined gravitational fields create 5 special points. In space, at these 5 points, a smaller object can sit in a kind of gravitational balance. These are called Lagrange points, named after the 18th century mathematician Joseph Louis Lagrange, who calculated them. The most famous Lagrange point is called L2. It's located about 1.5 million kilometers from Earth, directly behind Earth, from the Sun's perspective. At this point, the gravitational pull of the Sun and the Earth, combined with the centrifugal effect of orbiting, create a region where a spacecraft can orbit, with the Earth always between it and the Sun. This is very useful. A telescope placed at L2 can use the Earth as a shade, blocking sunlight and allowing it to observe the cold, dark universe without interference from solar radiation. The James Webb Space Telescope is located at L2. It was placed there deliberately to take advantage of this gravitational balance point. From L2, it can look deep into the universe in infrared light, with the Earth and Sun always at its back. The first L2 Lagrange point was calculated on paper. In 1772, the first spacecraft placed there came much later, and the James Webb Space Telescope, one of humanity's greatest scientific instruments, sits there now, held in gravitational balance, looking at the universe's first galaxies. Another interesting Lagrange point is L4 and L5, the fourth and fifth points. These are located in the same orbit as the smaller body, 60 degrees ahead and 60 degrees behind. At L4 and L5, an object can orbit stably. Jupiter has collections of asteroids at its L4 and L5 points. These are called the Trojan asteroids. There are thousands of them, quietly orbiting in the same path as Jupiter, 60 degrees ahead and 60 degrees behind, held there by the balance of gravitational forces. Gravity, as always, finding elegant arrangements, finding balance in seemingly unlikely places. 5 special points in every two-body orbital system, quiet pockets of equilibrium. Let's think about water and weight one more time. A cubic meter of water weighs about 1,000 kilograms. That's 1 metric ton. The oceans contain about 1.335 billion cubic kilometers of water. If you worked out the total weight of all that water, it's a number too large to intuitively grasp, but gravity is holding all of it, pulling all of it down into the basins of the ocean floor, keeping it there, year after year, century after century, through every storm and tide. Imagine the deep ocean, 2 kilometers down, 3 kilometers, 4. At those depths, the pressure is hundreds of times atmospheric. That pressure is the weight of all the water above it. The weight of the ocean presses down on everything at the bottom. Submarine volcanoes, ancient sediments, the strange creatures of the deep, all under that weight. And yet the ocean is also buoyant. The pressure that presses down also pushes up on anything submerged. This is Archimedes' principle. Buoyancy is simply the pressure difference between the bottom and top of a submerged object. The pressure at the bottom is greater than at the top because the bottom is deeper. That difference in pressure pushes the object upward. Whether an object sinks or floats depends on whether its weight exceeds the buoyant force. If the object is denser than water, if it weighs more than the same volume of water, it sinks. If it's less dense, if it weighs less than the same volume of water, it floats. Ice floats on water because solid ice is less dense than liquid water. This is unusual. Most solids are denser than their liquid forms. Water is one of the exceptions, and this exception is crucially important for life. If ice sank, lakes and ponds would freeze solid. In winter, from the bottom up, life in them would be destroyed. Instead, ice floats on top. It forms an insulating layer. The water beneath stays liquid. Life survives. This quirk of water, its unusual density relationship between solid and liquid forms, is tied to the hydrogen bonding of water molecules, and it happens to be essential for the persistence of aquatic life through cold seasons. Another quiet way that the specific properties of water, combined with gravity, made life possible on Earth. We mentioned earlier that gravity affects sound. Indirectly, let's be a little more specific. Sound travels differently, at different altitudes. Higher up in the atmosphere, the air is thinner. Sound travels more slowly. In thinner air, at sea level, sound travels at about 343 meters per second. At an altitude of 10 kilometers, the height at which commercial aircraft cruise, the air is much thinner and colder, and sound travels at about 300 meters per second. This matters for aviation, an aircraft traveling faster than the speed of sound at high altitude is said to be supersonic. When it crosses the threshold, it creates a shockwave, a sudden, large compression of air. That shockwave reaches the ground as the well-known sonic boom. The Kármán line, the boundary of space, is also relevant here. A Above about 86 kilometers altitude, the atmosphere is too thin for meaningful sound transmission. Sound essentially doesn't exist. Above that height, the vacuum of space is truly silent, no medium for pressure waves, complete stillness. In the acoustical sense, the phrase "in space, no one can hear you scream" is literally true. Sound cannot travel through a vacuum. All the sounds you hear, all of them, require the presence of air, and the air is held here, close to Earth's surface, by gravity. Without gravity, the air would drift away, the planet would fall silent. The ability to hear, the rich world of sound that surrounds you. Even now, even in this quiet moment, even the faint sound of your own breathing, requires gravity, requires the atmosphere that gravity holds, requires the medium through which sound can travel. Gravity, in the end, is even what makes sound possible. Let's visit neutron stars. One more time, briefly, because there's something extraordinary about them that we haven't mentioned. Some neutron stars pulse. They're called pulsars. When a massive star collapses to form a neutron star, the collapse happens very rapidly, and as it happens, the star's rotation speeds up enormously, just as an ice skater, pulling their arms in, spins faster. A collapsing star spins faster as its radius decreases. A star that rotated slowly, perhaps once a month, might end up as a neutron star, rotating hundreds of times per second. Neutron stars also have enormously powerful magnetic fields, millions of times stronger than any magnet we can create on Earth. These magnetic fields channel radiation, radio waves, X-rays, into beams that shoot out from the magnetic poles. As the neutron star rotates, these beams sweep around like a lighthouse. If Earth happens to be in the path of one of these beams, we detect a pulse of radiation. With every rotation, that's a pulsar, a spinning, pulsing neutron star, sweeping its beam across our detectors. Some pulsars rotate with extraordinary regularity. The first discovered pulsar, in 1967, pulsed every 1.3373 seconds, with such precision that the astronomers, Jocelyn Bell Burnell and Anthony Hewish, briefly thought it might be a signal from an extraterrestrial intelligence. They called it LGM-1, Little Green Men. Of course, it wasn't. It was a neutron star, but the regularity was that striking. Some millisecond pulsars rotate hundreds of times per second, with such stability that they rival atomic clocks for precision. All of this, the ferocious rotation, the intense magnetic field, the lighthouse beams, is the result of a star's collapse under gravity. Gravity compressing a stellar core into something 20 kilometers across, concentrating its rotation into dizzying speed, concentrating its magnetic field into something almost incomprehensible. Pulsars are gravity's most extreme, most precise timepieces, spinning in the dark, sweeping their beams, keeping time. We've mentioned that gravity bends light. Let's explore this a little more carefully. Light, as far as we can tell, has no mass. In Newton's framework, gravity acts on mass, so in principle, gravity shouldn't affect light. And yet, it does. Einstein showed why. In general relativity, gravity is not a force acting on mass. It's the curvature of spacetime itself, and everything, including light, follows that curvature. Light follows the shortest path through space, and if space is curved, that shortest path curves too. The sun's gravity, for example, bends the path of starlight that passes close to it. Stars near the edge of the sun appear slightly displaced from their true positions. Their light has been bent on its way to us. This effect is called gravitational lensing. More massive objects create more pronounced lensing. Gravitational lensing has become a powerful tool in astronomy. When a massive galaxy, or cluster of galaxies, lies between us and a more distant object, the foreground mass acts like a lens. It bends and focuses the light from behind it. Sometimes this produces multiple images of the same distant object, the same galaxy or quasar, appearing in several different positions around the lens. Sometimes it produces arcs of light, stretched, distorted, images of background galaxies. In some cases, the lensing is so perfect that it creates an Einstein ring, a complete circle of light, around the lensing object. Gravitational lensing can also magnify distant objects. It acts like a natural telescope, allowing us to see galaxies that would otherwise be too faint, too distant to observe. And gravitational lensing of dark matter, which interacts only through gravity, has been used to map the distribution of dark matter in the universe. By watching how background galaxies are distorted by foreground mass, astronomers can infer where mass is located, even when that mass is invisible. Light, bent by gravity, revealing the invisible, curves in spacetime, made visible as rings, arcs, and multiple images. The universe uses gravity as a lens to show us its own hidden structure. On the very largest scales, gravity organizes the universe into structures. Let's linger here. If you were to zoom out, way out, past our solar system, past the Milky Way, past the local group of galaxies, past the Virgo supercluster, you would begin to see the large-scale structure of the universe. It looks like a sponge, or a cosmic web, long filaments of galaxies, connected at nodes, where clusters of galaxies congregate. Between the filaments and nodes, enormous voids, regions hundreds of millions of light-years across, with very few galaxies. This structure, the cosmic web, formed under the influence of gravity, acting on the matter distributed throughout the early universe. Dark matter, in particular, is thought to have played a crucial role. The dark matter formed the skeleton of the cosmic web first, clumping along gravitational overdensities, ordinary matter, gas, and eventually stars and galaxies, fell into the gravitational wells carved by the dark matter. The filaments we see today are the traces of those ancient gravitational flows. Ordinary matter, streaming along the gravitational contours of dark matter, collecting at the intersections. The scale of this structure is difficult to hold in mind. The largest known structures in the universe are hundreds of millions of light-years across. The Hercules Corona Borealis Great Wall is estimated to be about 10 billion light-years across, and all of it held together, all of it shaped by the same gentle, universal force that holds you to the Earth right now. Gravity, just acting on scales of billions of light-years instead of meters. The same force, the same principle. Mass creates gravity. Gravity shapes structure. At every scale, from atoms to the largest things in the universe. Let's take a moment to think about falling differently, not with fear, just with curiosity. Imagine you're floating in space. No planet nearby, no star close enough to matter, just floating. You have no weight. There's nothing to fall toward. You're simply suspended, moving with whatever velocity you had when you arrived there. Now, very slowly, you drift toward a planet. At first far away, the pull is almost imperceptible. You're drifting very slightly faster, getting very slightly closer. Closer now. The pull is slightly stronger. You're drifting faster. Closer. Faster. The planet's curve becomes visible below you. The landscape visible. Atmosphere brushing you, gently at first. You're falling. Properly falling now. Pulled toward the center of the planet. But you have sideways velocity too. Enough that you keep missing the surface. Your path curves around the planet. You're in orbit, going around and around, falling and falling, and never quite landing. This is what a satellite feels. This is what the moon feels. This is what Earth feels around the sun. Falling always, but always sideways enough to miss. A graceful, endless falling, the universe's most peaceful motion. You can think of yourself, right now, as falling, not toward the floor, you're already there, but through space, around the sun, around the galaxy, in a state of continuous, graceful, gravity-guided motion. The Earth beneath you is falling too, together, always together, held by the same gravitational relationship, moving through space. As one, the light is low now. The world outside is quiet. Gravity is doing its work, pulling the air down around you, keeping the atmosphere close to the Earth, holding the moon in its orbit far above. The moon is up there right now, somewhere in its slow circle, moving at about 1 kilometer per second, quietly, unhurriedly, in the orbit that gravity gives it. The tides are moving somewhere in the world, water rising on some coast, retreating on another, following the moon's pull and Earth's rotation, patient as the sea always is. Somewhere a star is forming, a cloud of gas, many light years wide, slowly contracting under gravity. Centuries from now, at the center of that cloud, a new sun will ignite. Somewhere far away, 2 neutron stars are slowly spiraling toward each other, their orbit decaying as they radiate gravitational waves. In millions of years, they will collide, and the ripple of that collision will spread outward, at the speed of light in all directions. All of this is happening right now. All of it quiet, all of it gradual, all of it held together, shaped, guided, organized by gravity. The universe is very large, and very old, and very patient, and you are part of it. One small, warm, complicated piece of matter, held gently to the surface of a small, warm, complicated planet. The Earth pulls you, and you imperceptibly pull the Earth. Mass and gravity, always together, always there. You can rest now. The Earth has you. Let go. If you enjoyed this journey, if this quiet moment brought you calm, comfort, or wonder, please subscribe to the channel, gently tap the like button, and leave a comment to let us know you were here. Your support helps us continue creating these peaceful spaces for your mind, for your heart. Thank you for sharing this stillness, for being here. Until next time, rest well and let gravity hold you. Bye.